All right, today we're going to tackle one of the absolute biggest, most profound questions in all of science, a puzzle that has stumped the smartest people on the planet for more than 50 years. We are talking about P versus NP.
At its core, the whole P versus NP problem really boils down to this one simple-sounding question. Just think about it for a second. Is the creative spark, the act of discovery, fundamentally harder than just checking someone else's work? Or is there always some clever shortcut out there that we just haven't been smart enough to find yet?
You know what? Let's make this super concrete. Think about a Sudoku puzzle. If I hand you a completed grid, you can tell me if it's right in what? A few seconds. You just scan the rows and columns. Easy. But if I give you a blank grid and say, go for it, well, that's a whole different ballgame, isn't it? You could be stuck for an hour trying things, erasing, backtracking. That gap right there, between how easy it is to check and how hard it is to solve, that's the soul of this entire mystery.
And listen, this is not just some quirky academic puzzle. The Clay Mathematics Institute has a $1 million Millennium Prize just waiting for whoever can solve this. Yeah, that's how big of a deal this is.
So, to really appreciate the new breakthrough we're going to talk about, we first need to get a handle on the basics of this problem that's been around for half a century.
Okay, so let's get the terms straight. P stands for problems that are easy for a computer to solve. And by easy, we mean fast. Think about sorting a giant list of names. A computer can just blaze through that. And P stands for problems where it's easy to check a proposed answer. Our Sudoku puzzle is the perfect example of an NP problem. So, the million-dollar question, quite literally, is, are these two groups of problems actually the same thing? In other words, does P equal NP?
Now, inside that NP category, there's this special club called NP Complete. You can think of these as the final bosses, the hardest of the hard problems. The wild thing is, if you could find a fast way to solve just one of them, you'd automatically have a fast way to solve all of them. The classic example here is something called the Boolean satisfiability problem, or SAT for short.
So the problem was officially laid out way back in 1971. And for the next 5 decades, brilliant computer scientists and mathematicians threw everything they had at it and came up with nothing definitive. But just recently, a totally new argument has popped up from a field you wouldn't expect: physics. And this is where our story takes a really fascinating turn. It turns out the key to this huge computational puzzle might not be in pure math, but in the actual physical laws that run our universe. The core idea is kind of simple, but it is so profound. It's that computers aren't just these abstract logic machines. They are physical systems. They're built out of atoms, right? And because of that, they have to play by the rules of physics. And it might be those rules that are the real reason some problems are just fundamentally hard. Now, the key concept from physics here is something called a phase transition. You see this all the time. Think about water freezing into ice. One moment, it's a liquid, and then boom, at a specific temperature, its properties totally change. Well, it turns out that these hard computational problems have a very similar tipping point, a point where they suddenly switch from being kind of easy to solve to being an absolute nightmare. And as a problem gets closer and closer to that critical point, the correct solutions become like these tiny, isolated islands, just scattered across a huge, vast ocean of wrong answers. It makes finding one by just wandering around practically impossible. This brings us to the central idea of this whole new proof. This picture of a computational landscape filled with mountains and valleys that a computer has to find its way through.
I want you to picture this. Every correct solution is like a deep, calm valley. But to get from one of these valleys to another, you have to cross these massive mountains separating them. And these mountains are basically made of all the wrong answers. Physicists call them energy barriers. A regular computer has no choice. It has to start climbing step by step over these enormous mountains.
And this illustrates the difference perfectly. The computers we use every day, they're classical climbers. They have to take the long, hard road all the way up and all the way down the mountain. But a quantum computer, well, it could theoretically act as a quantum tunneler. It could just pass straight through the mountain. And that ability to tunnel is what would make it so incredibly powerful. So why can't our computers do that? It all comes down to a weird quantum property called phase. The easiest way to think of it is like the rhythm of a wave. Quantum particles have this, which lets them act like waves and interfere with each other. But our classical bits, our normal zeros and ones, they're more like tiny rocks. They don't have that wave-like phase. And with no phase, there's no wave, no interference, and absolutely no tunneling. They are stuck being climbers. So here's how this all comes together into a real proof. It's a pretty straightforward three-step argument. Step 1. The phase transition in these hard problems creates these gigantic energy barriers. Step 2. Because our classical computers don't have that quantum phase we just talked about, they are physically forced to climb them. And Step 3. The time it takes to climb those barriers just blows up exponentially as the problem gets bigger. The logical conclusion? P simply cannot be equal to NP.
Okay, so a proof that P does not equal NP isn't just a math curiosity. This has some deep, real-world consequences for everything from technology and science to even philosophy.
So why should you care? Well, for one, it means that struggle you feel when you're trying to solve a Sudoku puzzle is real. Discovery is genuinely, physically harder than just checking. It means that for tons of critical problems, like designing new drugs or planning shipping routes, there's no magic bullet algorithm out there waiting to be found. But you know what? That's also kind of liberating. It means scientists can stop chasing impossible dreams and instead focus their genius on creating clever workarounds that get us good enough answers.
This is maybe the most powerful way to think about it. This new argument says that P not equaling NP isn't just a rule for computers, it's a fundamental law of nature, just like thermodynamics. Right? You can't unscramble an egg because the universe tends towards disorder. And for the same kind of deep physical reason, you can't just magically solve these super hard problems. The universe itself seems to have a built-in bias that makes creating harder than checking.
And that leaves us with one final, pretty amazing thought to chew on. If the universe is literally built in a way that makes that flash of insight, that spark of discovery, fundamentally more difficult than just verifying someone else's idea, what does that tell us about creativity itself? It suggests that the slow, hard, often frustrating work of innovation isn't some flaw in how we do things. It might just be a basic feature of reality itself.